Okay, so it is a pleasure to present this talk, which is a joint work with Rustam Sadikov from the Kansas State University at this conference. I hope to come to Kiev one day in, I don't know, a year or two. So we will probably see each other in person. So the virtual nodes were introduced by Luke Kaufman. And what is the difference between them and usual nodes? Usual nodes are considered in R3 or another manifold, but virtual nodes are considered in the product of a surface cross R. So a surface is two-dimensional, and they're considered up to a slightly different equivalence relation. So the equivalence relation is isotopy, so basically this is a path in the space of smooth impedance, and stabilization, destabilization of the surface. So let me try to explain what this means. So assume that I have a surface, and I have a knot in it. So what I'm allowed to do is that I'm allowed to glue a handle which is away from the knot projection. Of course, it is a thickened handle. So, but I'm not going to talk about virtual knots. I'm going to talk about virtual Legendrian knots. And this requires to introduce what is a contact structure and what is a Legendrian knot. So contact structures are odd-dimensional analogs of symplectic structures. Symplectic structures appear when you talk about classical mechanics, and contact structures appear when you talk about geometric optics or light rays in the space-time. So contact structures exist on odd-dimensional manifolds, so the dimension of the manifold has to be odd. And by definition, it is a hyperplane distribution. So every hyperplane distribution locally is given the kernel of some one form, and the requirement is that the wedge product of this form with the alpha to the k is non-zero, so it is a volume form. So geometrically, this condition means that it is exactly the opposite of the Frobenius theorem. Frobenius theorem tells you that in some cases, you can find the submanifold of the same dimension as the plane or hyperplane distribution, which is integrable. So it is everywhere tangent to the distribution. The condition on the wedge product means that you pretty much do not have them. More precisely, the maximal dimension of the submanifold, which is everywhere tangent to the contact structure, is k into k plus one dimensional manifolds. So if you talk about the contact three-dimensional manifold, then the dimension of the maximal tangent submanifold is 1. And such submanifolds are called Legendrian. So Legendrian submanifold, by definition, is the submanifold of dimension k into k plus 1 contact manifold, which is everywhere tangent to the planes of the contact structure. So the classical example of the contact manifold is the spherical cotangent bundle of a manifold. So here, manifold can be of any dimension you wish, and the contact distribution is given as follows. Let's assume that you take an element in the spherical cotangent bundle. So what is this thing? So cotangent bundles is linear functionals on the tangent bundle. So spherical cotangent bundle means that you consider these functionals up to the multiplication by a positive number. Right? So a point in the spherical cotangent bundle is a linear functional on the tangent space to a manifold, considered up to multiplication by a positive number. But when you multiply by a positive number, the kernel of the functional does not change. So the contact structure is defined as the preimage under the differential of the projection from the spherical cotangent bundle M of the kernel of this functional. So this is my projection pi. It is a differential map, so I can take the preimage of the kernel of the linear functional to the differential. It will be a hyperplane, of course, and this is a contact structure. You have to check that this indeed satisfies the condition about the wedge product, but it does. So now what you can do is that if you have a Legendrian submanifold here, you can consider pyofil, which is usually denoted by a wavefront. So wavefronts are not immersed surfaces. So wavefronts have various singularities. They can have swallowtails, and they can have other singularities like cusp edges and double points. So they're quite singular. But they're equipped with a continuous normal vector field. So this continuous normal field has the following meaning, that if you look at a tangent space to this wavefront, it defines a linear functional, but not quite. Right? We want to define a linear functional up to multiplication by a positive number. So this means that you have to specify the kernel of the functional, which is this blue plane, and you have to specify the half space weight as positive, and this is given by the normal vector field. So now the virtual Legendrian knots were introduced by Dartmouth students Patricia Kahn and Daisy Levy, and what they are is that they are Legendrian knots in the spherical cotangent bundle of a manifold. But similar to usual virtual knots, they're considered up to the following equivalence relation, that you have this front projection, so to something like that, and it's equipped with a co-oriented normal vector field. And now what you can do is that you can change the genus of the surface by adding and subtracting handles far away from the projection of the Legendrian knot. So this is called stabilization and destabilization. And this is indeed the cusp. This thing, it is a solution to the equation x squared equal to y cubed. And cusps are generic singularities when you talk about Legendrian projections. So, of course, in the paper of Kahn and Levy, they introduced these Legendrian knots and links not necessarily for the case of surfaces, but for arbitrary manifolds, because it doesn't really matter whether the surface is two-dimensional or m-dimensional. You can look at Legendrian knots in spherical cotangent bundle of any manifold M, up to Legendrian isotopy, and up to the change on the spherical cotangent bundle, which is induced by any surgery on a manifold. So you can delete a handle, glue another handle as soon as it goes far away from the front projection of the Legendrian knot. This is fine. It's a big question. Assume that you have two knots which are not Legendrian isotopic in the spherical cotangent bundle of the manifold. Does this mean that they're not virtually Legendrian isotopic? It is not obvious at all that this would be the case, but we believe it will be, and I will try to provide some justification for why this might be the case. So why is it not obvious? Because if you have two Legendrian knots that are not isotopic in the spherical cotangent bundle of a sphere, what could happen is that you do surgery on the sphere, then you do surgery again, and in between you do Legendrian isotopes, then in the end you return to the situation where the base manifold is a sphere, and suddenly your two knots become isotopic. So what is the justification for this idea? So there is a theorem of Kuperberg. So what Kuperberg proved is that when you discuss the usual virtual knots considered by Kaufman, it is okay to monotonically simplify the surface, right? So assume that you have two virtual Legendrian knots that are living on surfaces of genus 2 and 3. And if they are virtually isotopic, this means that you can monotonically simplify the surface by deleted handles without any addition of the handles, till they become truly isotopic in the product of some surface by R. So we proved the similar theorem with Rustam Sadikov for two Legendrian knots in the spherical cotangent bundle of a surface. So it is essential that our proof is for spherical cotangent bundles of two-dimensional surfaces. We do not know how to generalize this to arbitrary manifolds, but we proved it. So in particular, the big question that I advertised about two Legendrian knots being isotopic, non-isotopic in the spherical cotangent bundle of the sphere implies that they're not isotopic in the as virtual Legendrian knots was proved by us if the dimension of the sphere is 2. But we don't know how to prove it in high dimensions. And strictly speaking, we do not really have probably enough evidence to say that we are sure it is true. This is just what we suspect. Now, wavefronts were heavily studied by Vladimir Arnold. And here is an important conjecture that was posed by Arnold, and it was solved by Yuri Chernov and Petr Pushkar. So the conjecture is the following: that assume that you have a usual Legendrian isotopia of an elliptic wavefront propagating inside to an elliptic front propagating outside. So you have a curve, the normal vector field specifying the Legendrian knot is pointing outside here and inside here. And what you do is that you prohibit what is called dangerous tangencies. So dangerous tangencies is a tangency of two branches of the front when the co-oriented branches, when the co-orientations point in the same direction. So this is a dangerous tangency because the two branches point to the same direction. This is a safe tangency because they point in the opposite direction. So what is dangerous about dangerous tangency is that this corresponds to the double point of a Legendrian knot. Right? So how do I get a Legendrian knot out of this picture? I consider the plane, or in this case, a line which is tangent to the two branches. This is the kernel of the two functionals. And the co-orientation direction, the normal direction, gives me the half space where the functional is positive. So here they would be positive in the same half space. So this is the same point in the spherical cotangent bundle of a surface. So this is a double point of a Legendrian knot. So what Arnold conjectures is that when you have an inversion of a wavefront, you necessarily have a moment when you have four cusps at the same time. So this was coming from the following picture, that if you have an elliptical front propagating inside, you will first get a fish like that. Then you will get a fish with two tails. Then these two branches become tangent and you get a quadragon, or whatever it should be called. Then these two branches become tangent and you will get a fish like that. Then you have a fish like this. And then it becomes an elliptical front propagating outside. So what is important is that there is a moment, namely here, when you have a picture with four cusps. So question that we pose with Rustam Sadikov is the following. Assume that you have a virtual Legendrian isotopia actually on any surface that transforms the elliptical front propagating inside to an elliptical front propagating outside. Does it mean that there will be a moment when you will have four cusps? We don't know the answer to this question, so this is a conjecture that it will. Right? So I mean that if you have an inversion of an elliptical front on an arbitrary surface in the category of virtual Legendrian knots, then you will have a moment when you have four cusps. So this is the picture that I already showed. Another important question that we have is the following. The Dink and Geiges, Van Dink and Hans-Jörg Geiges, proved the following fact, that if you talk about the spherical cotangent bundle of A2 with the natural quantum structure, and you have a core of the spherical cotangent bundle of A2, so you have a fiber with a point, and you have a cable of, well, I cannot draw a cable because I didn't leave space, so let us try to draw a cable. And if I draw a cable of this knot, once again, I'm doing something wrong. So how about I draw a blue cable? So I draw a cable of the knot. Then these knots are Legendrian, then this link is Legendrianly simple. So what does it mean that it is Legendrianly simple? So when you talk about the Legendrian knots, there are two classical invariants that are not truly Legendrian invariants. the Thurston-Bennigan invariant, which is essentially the self-linking number, because every Legendrian knot is framed. So it is a stripe rather than a rope. And another one is the so-called rotation number. So to be Legendrianly simple means that the classification of Legendrian knots in this topological class is given by two numbers, by the rotation number and by the Bennigan number, by the Thurston-Bennigan number. So we suspect that the same is true for virtual Legendrian knots. So let me formulate the question so that everything becomes more or less clear. So you have a cable of a fiber in the spherical Cartesian bundle, right? So you have so this is a fiber, and you have a cable, so it is something like that. So I once again did not provide enough space to draw it, but this is roughly speaking a cable. So what we suspect of this, if you consider a Legendrian cable of a fiber of the spherical Cartesian bundle, then it is not only Legendrianly simple, it is virtually Legendrianly simple. So when you consider virtual Legendrian links in this topological class, they're completely classified by the Thurston-Bennigan and by the rotation number, which do exist for virtual Legendrian knots. Right, so it is not completely obvious, but both the Thurston-Bennigan invariant and the rotation number do exist for virtual Legendrian knots. This is not a problem. They're well defined. And finally, the theorem that we actually have, this is not a question anymore. So at the previous talk at this conference, I discussed that Legendrian linking allows you to completely determine causality. So if you have a space-time, and you have 2 points, you say that they're causally related if you can get from one point to another without exceeding the speed of light. And what we proved jointly with Stefan Nemirovsky, is that 2 points in a globally hyperbolic space-time are causally related if and only if a certain Legendrian link is non-trivial. This link is formed by spheres of light rays through the 2 points I was mentioned a few seconds ago. So let me try to explain what is going on. So of course, everybody knows that when you talk about a point in a space-time, there is a light cone of light rays passing through it. But this light cone lives in a space-time. The linking happens in the manifold of all light rays. So space of light rays. And if you look at the cone that I described on this picture, you will see that it is foliated by light rays. So if you consider each individual light ray to be a separate point, because this is exactly what happens in the space of all light rays, then you get a sphere. The sphere is Legendrian, and it was conjectured by Notario and Todd and by Robert Lowe that this linking in some cases determines the causality, and we proved with Stefan that it pretty much always determines causality. Now, I will skip what is globally hyperbolic. It doesn't really matter much. But the important conjecture of Penrose is that all physically relevant spacetimes are globally hyperbolic. And our theorem with Stefan is exactly about globally hyperbolic spacetimes. So I skip the theorem with Nemirovsky. So let me try to explain the new conjecture. So there is a paper by Antoniou, Kaufman, and Labropoulos. So this paper pretty much does the following. It says that in their opinion, when you pass through singularity of a space-time, the topology of the space-like section changes. So basically you have some Cauchy surface before passing through the singularity, and then these two holes get united, and then you have one hole, something like that. Of course, this is exactly the setup when you should use virtual isotopy. And this is not the virtual isotopy in the sense of Kaufman, this is the virtual Legendrian isotopy in the sense of Patricia Kahn and Asa Levy. So by Legendrian, because the light cones, if you want to study causality, are Legendrian spheres. And we do not have a theorem in general. Actually, we do, sorry. So what we can prove is the following. Assume that during this deformation, which now works for all manifolds of all dimensions, not necessarily for dimension 2, assume that during this deformation, what happens is that either the universal covering of the section at the fixed time is not compact, or the integer cohomology is not the same as the one of the compact rank 1 symmetric space, and compact rank 1 symmetric spaces are basically projective spaces. So then Legendrian virtual linking determines causality. Right, so this is a theorem. So 2 points are causally related exactly if the corresponding Legendrian spheres are Legendrianly linked, provided that for all slices of the space-time which are changing with time, either the universal covering is not compact, or the or the integer cohomology is different from the compact rank 1 symmetric space. So how did this strange condition appear? This strange condition basically is Bott-Samuelson theorem. So Bott-Samuelson theorem usually is formulated for Riemann geometry, but at a certain moment, Stefan and myself realized that it is likely a quantum geometry effect. And indeed, this was proved to be a quantum geometry effect, not by us, but by Urs Frauenfelder, Claude Labrousse, and Felix Schlenk. So this is the end of the talk. I think that I'm exactly at my time. So do you have any questions?
Yes, it's time to conclude.
Yes, and I'm done.
Now, may I ask a question?
Sure.
Volodya, hello. Nice to meet you.
Hello, Sergey. How are you doing? I wanted to greet you after you talk, but I figured I should not interrupt the flow of the questions to you.
Thank you. May I ask you, you showed just down about deformations. You showed the surfaces.
This one.
Yes, this one. Because you know there is a paper by Osaku Saemi, you know, about the deformations of fold singularities. So, and that's at this position when this handle became from 2 handle, we became 1 handle. If you consider a family of these deformations, this might look as a function on a 3-dimensional, on one more dimensional manifold. And maybe these kinds of transformations, if you know precise normal forms of this, how to.
I think this is exactly what Antoniano, Kaufman, Lambropolo had in mind, that you consider some sort of a Morse function in the space-time, and if the Morse function is, you consider special time function. And if the time function is special, it will be a Morse function, and this will be Morse singularity. Yes,
but the problem is here is that usually you have, in some sense, two-dimensional deformation, because what if you draw this function in this kind, then you have a function like height function, and on the other hand you have deformation in this direction. And
yes,
maybe you look, maybe it will be useful. There is a notion of cobordism of Morse functions.
yes,
and this is precisely what this is actually a map of one model, no, m+1 dimensional manifold into R2. So in one direction, and this map should have fold singularities. Maybe this will be helpful because he find, at least for functions on surfaces, he actually computed the group of cobordisms. And they are described by deformations of Riemann graphs. So maybe
I think it will be very useful for applications, but I mean that let me try to emphasize a little that this is a theorem. The previous questions I was asking were questions. What I formulated about virtual Legendrian linking determining causality for such space-times is a theorem. Right? So I mean that it is probably useful for applications, what you're studying, what you're suggesting, but it would be but the theorem is proved.
Oh, okay.
We did not write it, but I mean that yeah, we know the proof. So are there any other questions? And thank you for the nice question, Sergey.
Thank you, Vladimir. You've been very interesting.